All right. Well, you gave away the trivia question. I was going to see if our audience knew what the actual angle on an angle polish connector was, but you gave it away. So
Uh, sorry.
8 degrees. That's all right. We can put it in the comments and see if anybody was paying attention.
That would actually be a good one. Um, Next one is temperature ratings. So the industry standard temperature ratings are commercial temperature and an industrial temperature. These values you see here, these are all in metric Celsius. So you're going from commercial temp, you're going from 0 to plus 70 degrees Celsius. And then industrial temp is rated for negative 40 to plus 85 degrees. And in some instances, I believe this might be true for remote PHY. I'm not 100% sure, but uh, there was a requirement to be beyond plus 85 degrees. So those should be operating between negative 40 and up to plus 92 or plus 95 degrees Celsius. That image you see there in our slide is a photo of our thermal chamber. So one of the things we do when we evaluate a manufacturer is we just put it in the oven essentially and run it for a week and see how it does. Is the wavelength stable? Is it transmitting at the same data rate? All that sort of thing.
So those are some pretty high temperatures. On the lower end, I think negative 40 Celsius and Fahrenheit are approximately the same.
Yep.
But on the upper end, when you get to 95 degrees of Celsius, that's it's pretty hot. It's just short of boiling in Fahrenheit. So you could cook an egg on something that's 95 degrees Celsius.
Yeah, you could.
So back to temperature or heat dissipation or power dissipation is very, very important.
Yeah, absolutely. Link budget. So I think, you alluded to this a little bit earlier. This might be something that the folks designing the network are more focused on, but certainly doesn't hurt to understand this from a field technician perspective either. So to plan your optical network, you need a budget. When an optic says 10 kilometers, this is really only a guideline. I've actually noticed that our 1 gig DWDM data sheets, the link budget, you know, the optic will be rated for 120 kilometers for a 1 gig, but that is factoring in an 8-channel mux on both ends. So in theory, if it was just a straight link, nothing else, like that 120 kilometers could be pushed a little bit further. But in some cases, if you're not using an 8-channel mux, you're using a 40-channel mux, and your passband loss is increased accordingly. I mean, you might not even get 120 kilometers. You might be lucky to get 80.
Right. So the design's really important. And from a field perspective, knowing what your link loss is, which may be different than what the original design budget is. I love the visual with the fiber loss, which is just normal optical attenuation, right? Versus all of the connectors, whether that be in the patch panel and the head end, and then your splice losses. You could have a field spliced mux in a can somewhere. Just knowing all of the parts of the path that can introduce loss into your optical link is really what determines what optic you put on either end. And to your point, the other considerations are, what is the data rate that you need? How far are you going? And then at some point, you have the Goldilocks zone that you mentioned is the receiver sensitivity, which you can also overpower a receiver, right? If you have too little loss and too much light, that you could potentially damage your transceiver.
Yep. And I'm actually, I think that might be the next couple of slides here where, yeah, so I kind of get into too much RX. So this kind of explains the Goldilocks zone a little bit. It's in this case we've got a 120 kilometer 1 gig CWDM. So this transmits at 0 to 5 dBm and has a receiver sensitivity of -32. So I would say, as a conservative estimate, this optic has about 32 dB of link budget. However, you see here though is the transmit power minimum is also the same as the receiver damage threshold. So if you ever are plugging in a signal into a 1 gig DWD or 1 gig CWDM optic, you want to make sure it's at least gotten some optical loss over that fiber. Otherwise, you do risk the receiver damage, where you actually just completely smoke the receiver, and now you've got a hat weight, not a transceiver. And then the next step through that is the input saturation power. So this one, because the optic could run as hot as +5, I like to tell people that you need about 13 dB of loss on this link before you can plug it in. So this kind of goes back to, you know, why is there a 120 kilometer optic? You know, why wouldn't we use it in a 10 kilometer deployment? Well, unless you've got 13 dB of loss in that 10 kilometers, it's not gonna link up. You're not gonna be able to transmit and receive data. And this is just one example of why.
So smoked optics, is that a technical term
That
or
is
a hat weight?
not, neither of those are technical terms. Those are definitely just some office terms. Smoke, basically, you have physical damage to the receiver, and there's no hope in repairing it. And hat weight, I don't know. I don't know if you guys use hat weights, but they make good boat anchors too.
Yeah, I don't know that I've ever heard the term hat weight, paperweight, all sorts of other things, but that's a good one. So the moral of the story is that there is a right and wrong transceiver for every application, right? Based on the the specifications or the characteristics of the transmit and receive sides, and the corresponding optical link budgets or losses in between them. So there is a right and wrong optic for every solution.
Yep. And so now, gonna kind of dive into all of the um, different types of SFPs, or primary different types of SFPs we see. There's a lot to kind of digest here. So type, you're going to see copper, gray, CWDM, DWDM. You'll often hear me refer to gray as also wideband. The reason for that is you'll see a data sheet for a wideband or gray optic, and it'll tell you, let's use the gray SX, for example. That's a short reach, 850 nanometer. But if you take a closer look at the data sheet, it's a wideband because 850 is the center, the average wavelength that's being transmitted. It can actually vary anywhere from 830 to 870. So hence why we call it wideband. And then you've got your maximum distances there, your medium, so Cat5, multi-mode fiber, and then basically almost every SFP except for the short reaches use single mode fiber. Connector, LC duplex, so pretty much every SFP that's on here uses LC UPC. There are some specialized transceivers called SFP BiDis, where those are actually LC simplex, where the TOSA and the ROSA on the transceiver itself are combined to act as what we call a BOSA, so it's a bidirectional optical subassembly. So on the same fiber, you'll have your transmit and receive, whereas the LC duplex will have the transmit and receive on separate fibers.
I got to admit, I'm a little surprised. I had never heard of an SFP for copper applications to transmit. I've always thought of SFPs as optical applications. So I learned something today that there is actually an SFP that I'm assuming is electrical to
Yep.
transmit over copper through Cat5 and an RJ45 connector. So that's kind of fascinating.
Yeah, it kind of surprised me too. The primary use case we see for those is for the management port of a switch or router. Oftentimes, you might see those ports already have an RJ45 connector embedded or a port embedded into them. A lot of the newer stuff, for whatever reason, they've put an SFP port in place there, and you can use copper or optical.
Well, I think it makes sense for all the same reasons, right? Because if that RG45 port ever goes bad in the backplane or the chassis itself, you don't have to replace the entire chassis, right? You can just replace the SFP
No,
and down the road you go.
that's true. Yeah, good point. So
So I'm learning a lot today, Yark.
I'm learning too. This has been good. I like it. That last column there, the lambda signal. So obviously for copper, we're not going to have an optical signal. SX, anything short reach is going to be 850. Your long reach is going to typically be 310. And then anything beyond your long reach, or what we like to just say is extended long reach, is going to be in the 1550 or C band. So CWDM, the primary channels that we see used in CWDM range from 1430 up to 1610. And then DWDM is basically all the wavelengths in the 1525 to 1570s, 1575 range. I'll explain some of that a little bit later, but just to like introduce the different hardware types, you see maximum distance. You can go as short as 100 meters, or you can go up to 160 kilometers with SFPs. You make the jump to 10 gig though, you can no longer get 160 kilometers. 80 kilometers is the typical limit. I do have 100 kilometers listed here. That is not really an industry standard. Basically, what we do there is if somebody really needs 100 kilometers, we just batch select a batch of 10 gig 80 kilometers, and out of a tray of 100 of them, one or two is bound to be hot enough for us to use for 100 kilometers. Yeah. Another thing
So
that you might notice. Oh, sorry. Go ahead.
yeah, so a bit of a nuance. So that's not really an industry standard, but it is something that Precision would offer if the use case required it.
Yeah. So another thing you may have noticed with 1 gig SFPs, the type typically said something like SX, LX, EX, ZX. That, and then you see with SFP plus 10 gig, now it's an SR, LR, ER, ZR. There's actually a rhyme or reason to it, and it deals with the encoding types or requirements that you see from 1 gig to 10 gig. So the X stands for external source coding, which is your 8-bit, 10-bit coding encoding. I feel like I can't talk about that too intelligently, so I'm just going to just state it and not go too in depth on it. But when you get to the 10 gig, it is, oh boy, I'm trying to blank on this. So the X is external source coding. Oh, R stands for scrambled encoding, which is 64 bit 66 timing, which is a requirement for 10 gig. There's pages upon pages of Wikipedia pages that can explain that a whole lot better than I could, but there's Long story short, just there is a difference between a 1 gig and a 10 gig in terms of type. If you see an X, it's probably a 1 gig. If it's LR, if it has an R, that's a 10 gig. But something we do also see when we get to 10 gig is the introduction of a couple of different types of technologies. So whereas 1 gig we had copper, gray, CWDM, DWDM. When you get to 10 gig, you see the introduction of 10 gig tunable. And we also see the introduction of DACs and AOCs. DACs stand for direct attach cables. AOC stands for active optical cable. So with a DAC, that's actually, I have an entire slide on this. There. What is an active optical cable? What is a DAC? So optical cable, the optical fiber cable is hardwired into a transceiver on both ends of the link. A DAC is where there's actually a copper cable hardwired into both ends. And I realize the formatting of that photo is cutting off some of the
Yeah, the
text
words
there.
and the DAC description, but I think we get the point. And I think those are obviously indoor, limited use, specific application type things, more so than I think more of what we're starting to see in the field is those SFP plus tunables that
Yep.
have a huge benefit, right, in how many spare transceivers you have to keep on your truck to, for whatever DWDM wavelength that device has to have, to being able to carry tunables that can be basically tuned anywhere in the C band as needed. So if your SFP fails for whatever reason, or new plant activation as you're turning stuff up, it really helps allow us be more dynamic in utilizing all of the MUX ports and different wavelengths over a single fiber. So that DWDM tunable SFP plus is kind of a big deal.
Yeah.